Okay, I just want to talk you through a couple more points on calorimetry and specific heat capacity for calorimetry. So this next little example just kind of walks you through specific heat capacity, just as a check to make sure that you are like making the connection between all of the different variables. So it would be a good one to pause, try it, and see if you can beat me there. All right, so they're asking for how much heat is needed. They want you to warm 250 grams of water from 22 degrees Celsius to 98 degrees Celsius, and they give you specific heat capacity of water. So you can do this one of two ways. You can set up the formula and plug and chug, right? So that would look like specific heat equals Q over M delta T, and then we're looking for heat, so we want C times M times delta T equals C. So you solve for the variable you're looking for, you plug and chug, and we're all happy. Now, going about the problem this way necessitates that you have the formula memorized. And as usual, I do not advocate you memorizing the formula. So let me show you a different way of going about this. Notice that we're given the specific heat capacity, 4.18 joules per gram Kelvin, right? We can approach this through dimensional analysis and therefore avoid memorization. So to do that, I'm just going to identify all of the variables that I don't want and try to eliminate them out. So I'm looking for heat. The unit on heat is joules. So I want to get rid of grams and Kelvin, and I want to keep joules. So to get rid of grams, I'm just going to multiply 250 grams. So grams disappears. To get rid of Kelvin, I need to multiply by the change in temperature in Kelvin. So 273 plus 98 is 371. 273 plus 22. 371 minus 295, 76. Okay, so 76 Kelvin. Now, you don't always have to convert between Celsius and Kelvin. There are times where you're looking for a specific difference, for example, and that difference is going to be the same in Celsius and also in Kelvin. But my policy is I don't really want to have to process through that on the test, so I just convert into Kelvin always. That's my kind of approach. You certainly don't have to use that approach if you think thinking through it and not converting saves you time. That is totally fine too. Okay, so anyway, I multiply by the difference in temperature, getting rid of Kelvin, leaving me with joules. And I get my answer, 79420 joules. So either way, you're going to notice that the math ultimately gets set up either way. One way you have to memorize a formula and plug and chug. The other way you kind of logically approach it through dimensional analysis. No memorization needed, but you definitely have to know what all those units represent. Okay, so there's my answer. You should be keeping that to two significant figures. So it would round to 79000 joules in terms of significant figures. B, what is the molar heat capacity of water? Okay, again, would be a good time to pause here and see if you can get yourself from heat or specific heat into molar heat capacity. See if you can beat me there. All right, so basically I'm in specific heat capacity, 4.18 joules per gram Kelvin. And instead of being in grams, I just want to be in moles. So I'm going to convert out of grams of water and into moles of water. I think it's 18.08, right? Oh no, 1.008 times 2 plus 16, 18.016. Grams per 1 mole of water. So grams disappears, and now you have joules per Kelvin mole, which is the molar heat capacity instead of the specific heat capacity. Ta-da! Okay, we'll try this one together in class. Just a couple more concepts. So we have been talking about constant pressure calorimetry, right? That's why we can talk about heat instead of work. Okay, so in order for us to talk about the heat transfer without considering the work, remember a couple conditions have to be met. First of all, atmospheric pressure has to remain constant, which it will as long as you have an open container. In this case, we are working, our total energy transferred is going to be the heat. We get to ignore work because it's under constant pressure. And so since we're talking about the transfer of heat, we are talking about enthalpy. We're talking about the transfer of the enthalpy of reactions. So if you're talking about a neutralization reaction, you can find the enthalpy of neutralization. If you're talking about a salt dissolving, you can find the enthalpy of dissolution. If you're talking about burning something, you can find the enthalpy of combustion. So in all of these cases, since it's under constant pressure, we are going to be finding enthalpy of the reaction, whatever reaction we're talking about. In order to do this, we are going to assume there's no leaking out of our calorimeter. So all of the energy is going to be contained within the calorimeter. You can look at a couple advanced problems where you look at the heat loss to the calorimeter. But in order for this idea to work, you basically have to seal in your heat fairly well and then assume that there's no leakage between containers. This is what our lab is going to center on. It's going to center on calorimetry, and so you'll see what I mean by this. Remember, we're getting back to these terms of endothermic and exothermic. Endo is going to be energy going into your system, whatever that system is that you're looking at. Is it a piece of food? Is it a piece of metal? Is it a salt? Is it a reaction? Whatever it is, endothermic would be energy going in or heat going into that system. Exothermic would be heat leaving. Exothermic, your Q is going to come out negative since heat is going from the system to surroundings. Endothermic, the Q is going to be positive since heat is going from surroundings into your system. But whatever the case, we're basically assuming a perfect transfer of energy. So whatever the solution, whatever the reaction gives off in terms of energy, the solution is going to take on. So the Q of the reaction is going to be the same magnitude as the Q of the solution. It's like if I hand you 4 oranges, right? I am losing 4 oranges. You are gaining 4 oranges. Our magnitude is the same. The signs are opposite. Whatever the reaction gives off, the solution takes in. Whatever the solution gives off, the reaction takes in. They're going to be equal in magnitude, opposite in sign. Lastly, we're going to assume that the specific heat of solutions is going to be close enough to the specific heat of pure water. And whenever we're dealing with dilute solutions, this actually is true. So we'll keep our solutions dilute enough so that the specific heat of whatever solution we're dealing with, we can just use the specific heat capacity of water. All right, we'll try this together in class. Last note here on calorimetry. So we've been talking about constant pressure calorimetry. There is a non-constant pressure calorimetry, a pressure variable calorimetry. It's called bomb calorimetry because essentially that's what you're making. You're making a little bomb because you're building up pressure inside of a container. Right? So this would be constant volume calorimetry. The volume stays consistent. The pressure changes. A lot of times these are used for combustion reactions. So they pump in oxygen to this little thing, and then they burn whatever organic compound they're looking at. Notice in this case, the heat evolved is going to be total energy. It's not enthalpy because the pressure is not constant. We can't talk about enthalpy. So notice here's the contraption down here. Inside this container is where the combustion occurs. See these little wires here? These are used to ignite the reaction. And it's a steel bomb. It's a steel little container so it can withstand the force of the pressure increasing. And then it's made out of metal so that the energy can transfer into this water really easily. So the whole little steel bomb there is surrounded by water. And then notice that they're taking the temperature of the water itself. So they're going to track how much heat the water absorbs, and whatever heat the water absorbs is going to be equal in magnitude, opposite in sign as whatever the combustion reaction gives off. You have to know the capacity of the calorimeter. So that means how much energy does the calorimeter absorb before it changes a degree in temperature. And that way you can figure out how much the heat the reaction actually gave off. So just to let you know, we don't deal with that a whole lot in our curriculum, but it does exist. It is a thing. And this is what it would look like. And they would call it constant volume calorimetry or bomb calorimetry. Okay, so that is all of the concepts that I want to kind of touch base with before we jump into calorimetry. After we kind of deal with calorimetry and hash out our practice problems, go through the lab, then we'll go on to the rest of Chapter 6 and merge into Hess's Law. So hang in there. I'll see you in class.